This is my beginning algebra course. Today we're going to simplify expressions with square roots. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. We haven't learned square roots yet. This is asking what number times itself is equal to 49. What number times itself is equal to 49? And if you said 7, you're correct. So this number is asking what number times itself is equal to 16. Or this expression is asking what number times itself is equal to 16. If you said 4, you're correct. So that's what these roots are. Now these are square roots. We're not going to learn any other types of roots in this course. You'll learn other types of roots when you take intermediate algebra. And that's what this is. So if you take the square root of 49, we get 7. And the square root of 16 would be 4. So try number 25. What is the square root of 25? In other words, what number times itself is equal to 25? If you said 5, you're correct, because 5 times 5 is 25. So what this is it's the opposite of squaring. So if you take 9, for example, and you square it, you get 81. But if you start from 81 and you want to go backwards, you square root it to go back to 9. So square rooting is the opposite of squaring. And again, just in case we didn't talk about this enough, squaring is the same thing as raising to the second power. It's just a special way to describe it. And if you cube a number, if you raise 9 to the third power, that's called cubing a number. And the reason that it's called squaring is because if you want to find the area of a square, you multiply the side length by itself. And if you want to find the volume of a cube, you multiply the side length by itself 3 times. So that's where the words square and cube come from, but that's not really important for this class. There's one more thing that I want to mention before we proceed with the rest of these problems. You may have wondered, why isn't it 7 or negative 7? Because it's true that 7 times 7 is 49, but it's also true that negative 7 times negative 7 is 49. Well, the reason that we don't the reason that one of the answers is not negative 7 is this notation is just defined to be positive. It's a positive number. So that's just a definition. That's just tradition. Whenever you see a square root of a number, your square root is always going to be positive. Again, there's no interesting answer to that other than just it's tradition. That's what the notation means. So in case you're wondering about that, that's the explanation. It's always assumed to be positive. All right. So why don't you try number 4? Again, we're looking for the square root of 81. That's how you read this, the square root of 81. And what that means is they're asking what number times itself is equal to 81. So go ahead and try that problem, and when you come back, we'll do it together. All right, we're back. If you said 9, you're correct. And what about, again, because that's 9 times 9 is 81. So that's why it's 9. So try number 5, and when you come back, we'll do it together. If you said 2, you were correct. Try number 6, and when you're done, we'll do it together. All right, we're back. It's 10. So if you got 10, good job. Try number 7. All right, if you said 8, you're correct. Try number 8. And if you said 3, you're correct. You can pause the video if I'm going too fast here. Try number 9. Now number 9 is actually going to be a little tricky. So see if you can figure this out. If you can't, that's okay. We'll do it together. But what number times itself is equal to 1? Pause the video and think about that. And when you come back, we'll do it together. All right, we're back. If you said 1, you're correct. Because 1 times 1 is 1. So that was kind of a tricky problem. Now try number 10. If you said 6 for number 10, you're correct. So as you can see, finding square roots is pretty easy. It's not difficult at all. Now also be aware that these are sometimes called radicals. I'm not going to call them radicals in this class, but that's another name for these symbols. Now, the reason that it was easy to find all of these square roots is because these numbers were what we call perfect squares. What that means is these numbers were the result of squaring a whole number. So let me show you what I mean. 1 squared is 1. Actually, let me write this horizontally. 1 squared is 1. 2 squared is 4. 3 squared is 9. And I'm going to put commas here. 4 squared is 16. And 5 squared is 25, so on and so forth. These are perfect square. The numbers down here are perfect squares because they're the result of a number, of the square of a number. And we have 5 squared is 25, and 6 squared is 36, and so on and so forth. So I'm not going to write all of them, but these numbers in the yellow are perfect squares. So when you try to find the square root of a perfect square, it's really easy because you just go back to these numbers here. That's why it was easy to find the square root of the problems that we did in problem numbers 1 through 10. But look what's going to happen as we go down to number 11. Now they're asking us find the square root of 3. How in the world are we going to do that? That's not easy. In fact, in order to do those calculations, we would need advanced mathematics. So we don't have the math that we need at this level, the beginning algebra level, to do that without a calculator. So we have to use the calculator. So what you're going to do is you're going to, you want to get your calculator and you want to put it in landscape, rotate that phone or whatever you're using, and put it in landscape mode. And I'm using an iPhone, but it's going to be a similar type of it's going to be a similar buttons for your whatever other phone you're using. And it's going to be similar buttons probably for your calculator. But what you're going to do is you're going to enter in 3, and then so you're going to push the 3 button, and then you're going to push a button. And again, it's going to be slightly different depending on what you're using. But on my iPhone, I have this button. This is the calculator that's built in, that comes with the phone. So you're going to push 3, then you're going to push this button, and that's going to give you your answer. So it's very easy. So I'm going to go ahead and do that. And I'm going to put an approximately equal to sign. So if you do that, you end up with a decimal that is it said that it does not terminate. It never ends. It just keeps going on and on and on and on. So we can't write the entire decimal because it doesn't terminate. It just keeps going on and on and on and on. Not only that, not only does it not terminate, but the decimal has no repeating pattern. So when a decimal doesn't terminate and it has no repeating pattern, it's called an irrational number. So these are all irrational numbers. But the important thing to understand is we need to use the calculator to find these, and we have to approximate. So why don't you try the next problem? Instead of 3, you're going to plug in 15, and then you're going to push this button. And I want you to round off to the nearest 100,000th place. So that's the 5th number over. So round off to the nearest 100,000th place. So try number 12, and when you come back, we'll do it together. All right, we're back. So I'm going to enter in 15, and then I'm going to push that square root button, and I get 3.8729, and one more 8, and there you go. So if you got that answer, good job. Make sure to rectangle all your numbers. So try number 13, and when you come back, we'll do it together. All right, we're back. I got 1.41421. So if you got that answer, good job. Try number 14, and when you come back, we'll do it together. All right, we're back. I got 2.64575. So if you got that answer, good job. Just be sure that you're writing your approximately equal to signs. Don't write an equal to because it's not technically equal to. It's only approximately equal to. All right, so try 15, and when you come back, we'll do it together. All right, we're back. So I'm going to plug in 97 to my calculator and then push that button, and I get approximately 9.8488, and this is the first problem where we have to actually round up. Now, if you forgot how to do rounding, in these problems we rounded down because the number to the right of the hundredth place was less than 5. So in all these cases we rounded down. But in this last problem, the number to the right of 8 is actually 7, if you look in your calculator. So the 7 tells us that we're going to round the 5 up. So the 5 is going to become 6. So again, if you want to review rounding, just look to my arithmetic course in the class on rounding. All right, so those were irrational numbers. That's when we're trying to find the square root of a number that's not a perfect square. As you can see, it's pretty sophisticated stuff. Your calculator has to do some sophisticated algorithms to come up with the answer there. All right, so on to the next problems. I'm going to drag this thing with us. Actually, I can just leave it there for now. So now we're going to take the square root of a fraction. Now this probably seems like it's going to be really difficult, but it's actually not difficult at all. So now let me give you an example. So let's say that we're going to, let's see here, let's say we're going to take 8 over 9 and we're going to square it. Squaring means that we're going to take 8 over 9 and multiply it by itself. That's what squaring means, raising to the second power. So now you know that when you multiply fractions, you just multiply straight across, right? No big deal. So then you get 64 over 81. Now what if you want to go backwards? What if you want to go from here to here? Or excuse me, we should start out with the, let me shrink this here, I don't want to confuse you. So 8/9, and then we're taking it and we're squaring it. So what if we want to go from here to here? We want to go backwards. So you want to take the square root of 64 over 81. Well, what we're asking is what number times itself is equal to 64 and what number times itself is equal to 81. Because you're just multiplying straight across. So you just need to square root this number to get back to 8 and square root this number to get back to 9. So what that means is when you square root a fraction, the square root of some fraction a over b is equal to the square root of a over the square root of b. Now I know that this probably is very intimidating to you. It's going to make you nervous. Okay, you're going to think, well, that looks really complicated, and I don't know if I really understood that explanation. Well, it's okay. It's okay. 99.99999% of students, math students, and teachers don't really think about why this is true. They just memorize it. So the primary purpose of this course is to learn fluency in the language, not to study why this theorem works. Now it's good, or this principle. Now it's good to study why the principle works. It's just the number one priority is to learn how to use it. Now again, I know you're going to think that sounds really dumb. You know, it seems like you should learn why it works. Well, that's correct. It's good to learn why the property works, but you need to learn how it works first. You're going to figure out how to use this in problems, and then if you want to, somewhere in the future, you can go back and figure out what it is. But when I tell you that students don't really think about it, I'm not exaggerating. Really, they don't think about this. They just memorize the rule, and that's all you're really required to do in pretty much any beginning algebra course. Doesn't matter how prestigious the school is or how good the teacher is. This is just how it's done in the academic system. I'm not saying it's right or wrong. I'm just saying you need to learn fluency. That's the primary objective. So we're going to take this property here. We're going to keep this with us. So I'm going to put it over here so get it out of the way. So the square root of 9 over 25 is equal to the square root of 9 over the square root of 25. And the square root of 9 is 3. The square root of 25 is 5. So there you go. It's easy. So that's what this principle tells us. Now again, if you didn't understand all that explanation, you don't need to understand it. Please understand. Please don't be intimidated by all that. Don't be discouraged thinking that you need to understand the explanation. You're not required to know that. All right, so the square root of 1/4 is square root of 1 over the square root of 4. If you want to take the square root of a fraction, it's the square root of the numerator over the square root of the denominator. That's what this says. So the square root of 1, we learned that in a previous problem. The square root of 1 is 1. The square root of 4 is 2. There you go. Easy. So again, if you want to take the square root of a fraction, the square root of a fraction is equal to the square root of the numerator over the square root of the denominator. That's what this principle is telling us. And we have one more principle that we're going to learn. We're not going to do that. We're not going to do it right now, but the other principle we're going to learn is the square root of a times b is equal to the square root of a times the square root of b. These are the two principles that we're going to use in this class. So we're going to keep these with us as we go along in the class. But we don't really need this one right now. I'm going to get rid of that. All right, so why don't you try number 18, and when you come back, we'll do it together. All right, we're back. So the square root of a fraction is equal to the square root of the numerator over the square root of the denominator. And what number times itself equals 36? That's 6. What number times itself equals 49? That's 7. 6 over 7. All right, so try number 19. If you got 6 over 7, good job. And try number 19, and when you come back, we'll do it together. All right, we're back. So if you got 1/4, good job. Again, we're using this principle up here. Don't forget this. Don't forget this this property. I'm going to color it green. Actually, I'm going to color it blue. So that colored property there, don't forget that. That's what we're using here. So try number 20, and when you come back, we'll do it together. All right, we're back. So if you got 9 over 2, good job. All right, try number 21, and when you come back, we'll do it together. All right, we're back. All right, so if you got 10 over 3, good job. All right, so now we're going to use the second principle that I was talking about. Now we're going to use the principle that the square root of, we learned the square root of a over b, the square root of a divided by b, is equal to the square root of a over the square root of b. So this was a division principle. But now we're going to use a multiplication principle. The square root of a times b is equal to the square root of a times the square root of b. So this is the second principle that we're going to use. And I'm going to color this one green. All right. Actually, I'm going to get that a little smaller there. I don't want to take up too much room. And I'm going to need to get this out of the way. All right, so now we're going to do something called factoring out a perfect square. Now, this number here is not a perfect square. We can't find the square root of 12 very easily. So we can't really just find the answer immediately, but we can simplify the expression. We can make it to where it's easier to work with. So what we're going to do is we're going to pull out a perfect square using this principle. So what we're going to do is we're going to factor 12 to 4 times 3. Now I could factor 12 to 6 times 2. So why am I choosing 4 times 3 and not 6 times 2? Well, in order to factor out a perfect square, we need one of the factors to be a perfect square. 4 is a perfect square. So let me get my list of perfect squares. And I'm sorry to bore you by giving this explanation, but you know, one way to do it is just to show you and just to shut up and show you, but I want you to know exactly what's going on here. Some students will complain if you just do the problem without explaining it. The best thing really is just to do the problems, and you'll get the hang of it as you go. But like I said, some students want you to explain immediately. So these are our perfect squares. And you don't really need this list, and that doesn't look like a 4, so I'm going to change that to a 4. You don't really need this list. You can figure out what the perfect squares are just by taking the whole numbers and squaring them. See how I'm squaring all these numbers in the pink? So if you square all those numbers, you get what are called perfect squares in the yellow. So you don't really need to memorize the perfect squares, because you can just, again, you can just square the integers, and you get the perfect squares in yellow. So 4 is a perfect square. So that's why I factored 12 to 4 times 3 instead of 2 times 6, because I'm going to pull out a perfect square. Let me show you what's going to happen. So look at the green over here. You see the green? So we're gonna use this principle. We have square root of AB is equal to square root of A times square root of B. We have A and B. So I'm letting 4 be A and 3 be B. So we have square root of 4 times square root of 3. So I changed this to this using the green principle here. So at that point, we can then, the reason that I did that is because this is a 4 is a perfect square, and that means that I can easily square root it. What number times itself is equal to 4? What number times itself is equal to 4? Well, that's 2. So I pulled out a perfect square. I factored 4 out of 12, and then I pulled it out of the square root. So that's what I mean when I say we're factoring out a perfect square. And now the expression is easier to deal with because the number inside the root is smaller. We had 12, but now we have 3. Now, if I had tried to factor using 6 times 2, there is no perfect square. Neither 6 nor 2 are in this yellow list here, so we cannot pull out a perfect square if we factor it to 6 times 2. So just be aware. When you factor, you're looking for the perfect square. There may be more than one way to factor, but you want the perfect square. So we're not going to use this method, or this factorization. All right, so there's one more thing that I have to say. You're probably loaded up with information at this point, too much information, but another important thing to understand with roots is, you see how we wrote this dot here? We don't need that dot. We can show the multiplication just by putting 2 right next to the root 3. This means 2 times root 3. And that really angers a lot of students seeing this, because students want to see a sign for multiplication, a symbol for multiplication. They want to see 2 with a cross, 2 times root 3 with a cross. They want to see 2 times root 3 with parentheses. It really annoys students that we're putting the root right next to the number. So, but that's just something you're going to have to get used to. When you put a number right next to a root, it means multiplication. So I'm not going to write this dot anymore. I'm not going to write this dot anymore between the root and the number. I'm going to skip that step. So I know that's a lot of information we just went over, but don't worry, we're going to do tons and tons and tons of these problems. So if you didn't understand anything that I just said, that's okay. I'm just giving you a little introduction. So now we're going to have a chance to do a lot of these problems, and you'll get the hang of it. Fluency is the primary objective here. Giving a detailed explanation, that really doesn't matter. All that matters is that you can do these problems. And you're going to learn how to do that right now as we do tons and tons of these problems. So let me move this over a little bit. All right, so let's try root 18. So we're going to do this one together. So I could factor to 6 times 3, but neither 6 nor 3 is in this yellow list here. So I'm going to try factoring 9 times 2. And I know that's going to work because 9 is one of the perfect squares in this list. So now I'm going to use the green principle here. You see this green principle? I've got the red line around it, so I'm going to try to shrink that a little bit, move it over. I'll just keep it down here. So we're going to use the green principle. We're going to separate. And this is a perfect square. That's why I factored to 9 times 2 instead of 6 times 3. What number times itself is equal to 9? What number times itself is equal to 9? If you said 3, you're correct. So then we just can get rid of that dot and we can just write root 2. In fact, we don't really even need these dots. You'll see roots right next to each other like this, and that just means multiplication. You don't really need the dot. I'm just writing the dot to reduce confusion. All right, so that's the answer. So 24, why don't you see if you can try 24? If you get stuck, that's okay. We'll do it together, but go ahead and see if you can try 24. You need to use this principle here. You need to factor 27, and actually when it comes to 27, there's only one way to factor it. So this is a good one for you to start out with because you don't have to worry about alternate factorizations that don't work. So try number 24, and when you come back, we'll do it together. All right, we're back. So we're going to factor to 9 times 3. That's the only way to do it. There is no other factorization. So then you use the green principle, break it into break the root apart. And square root 9 is a perfect square. It's in the list. So we go to 3 square root 3. And by the way, I didn't mention that you see these leftover numbers inside the roots. Again, we talked about this. We can't do anything with that. We just have to leave it there because those numbers are not perfect squares. So the perfect squares came out, but the leftover numbers, they cannot come out of the root because they're not perfect squares. All right, so if you got 3 root 3, good job. So we're going to do a ton more problems. So don't worry about it if you didn't catch on with those first problems. We're going to do a lot more. So let me take these equations and lists, put them up here. So keep these colored properties in your field of view here. So now, see if you can try 25, and don't worry if you get stuck. We're going to do them together. So try 25, and when you come back, we'll do it together. All right, we're back. So that becomes 4 times 2. Use the green principle, and we have root 4 times root 2, and then root 4 is just 2. That's a perfect square. So if you got that answer, good job. So in that example, there was only one factorization, 4 times 2. There wasn't really any other factorization. You could have done 2 times. You could have gone too far, 2 times 2 times 2. But as you can see, if you went that far, there's definitely no perfect square. 2 is not a perfect square. All right, so for number 26, again, there's different factorizations you could choose, but you want a factorization that contains one of these yellow numbers up here, 1, 4, 9, 16, 25, or 36. So go ahead and try 26, and if you get stuck, we can do it together. All right, we're back. So I could factor into 3 times 30. 3 times 30 is 90, but again, neither of these numbers are on this list, so that's not going to work. I want to pull out a perfect square. Neither 3 nor 30 are perfect squares. So what else could I do? I think I could do 6 times 15. And by the way, you're probably thinking, well, how do you know it's 3 times 30? Did you use a calculator? Well, you can use a calculator. You just take 90 divided by 3 and you get 30. So 3 times 30 is 90. 90 divided by 3 is 30. 30 times 3 is 90. If you divide 90 by 6, then you get 15. So let me just write this out. So that's one factorization. Another factorization is 6 times 15. Again, you can divide 90 by 6 and you get 15, so that's how we know. You can use a calculator in this class because we're going to get to some big numbers. You see these numbers down here? We're going to get to 125, and we're going to get to 275. So you're allowed to use a calculator. You need to divide so that you can figure out what these factor trees are going to be. So, but we're not going to use these factorizations because look, neither 6 nor 15 nor 30 nor 3 are on this yellow list. We're looking for a perfect square, so we need to find that perfect square. And if you found that the perfect square is in the factorization 9 times 10, then you're correct, because 9 is on the yellow list. So now we use the green principle here, and we break it up. We break the square root up, and the square root of 9 is 3, and we just put the root 10 right next to it. So if you got 3 root 10, good job. If you got stuck there, that's okay. We have a lot more problems to do. So for number 28, go ahead and try that. And again, if you get stuck, we can do it together. All right, we're back. So I could factor 28 to 2 times 14, but again, neither 2 nor 14 are on the list. And let's see, what else could I do? I think that's pretty much it, except 4 times 7. That's the correct factorization. So 4 times 7. So we're going to break it up using the green principle. So keep your green principle in the view there. Root 4 times root 7. And root 4 is a perfect square. That's why this works, because root 4 is a perfect square, and that becomes 2. So if you got 2 root 7, good job. Now notice that I'm putting the number to the left of the root. You might be wondering, well, what if I factor this number? What if I factor it to 7 times 4 and then break it up, and you end up with root 7 and the 2 is on the other side? Is that okay? I would say this is not okay. If you want to put it in parentheses, then maybe it'll be okay. If you put both of them in parentheses, that would be even better. But it's very risky to just put the 2 on the right, because a lot of students will accidentally interpret it as root 72. So you want to stay away from that. It's very unusual to write the number on the right side of the root, so please don't do that. To avoid that, you want to write the perfect square. When you do the factorization, always write the perfect square at the very left. So again, I know this is a lot that we're going over right now. There's a lot there's a lot to remember, but that's okay, because we're going to do so many practice problems. All right, so for number 44, go ahead and try that one, and when you come back, we'll do it together. Excuse me, number 28. All right, we're back. So we could do 2 times 22, but neither of those numbers, neither of those factors are perfect squares. They're not on the yellow list. So we're going to do 4 times 11. Use the green property to break it up. And then square root of 4, that's a perfect square. And again, the reason we use this factorization is because 4 is on the list. That's in the yellow list. So square root of 4 is 2, and then so on and so forth. I think you get the point. So if you got 2 square root 11, good job. All right, so for 54, there's quite a few ways to factor 54. So see if you can pull out a perfect square. Again, we're looking for one of these yellow numbers. So try number 29, and when you come back, we'll do it together. All right, we're back. So we could do 2 times 27, but those numbers are not perfect squares in the yellow list. And we could do, let's see, I think 3 times 18 works. 3 times 18 is 54. But again, neither 18 nor 3 are perfect squares. They're not on the list. But if we do 9 times 6, 9 is on the list. So now we use the green principle up here, the green principle, to break it up into 2 parts, break up the root, and square root 9 is 3. So again, the reason we use this factorization is because we can pull out these yellow perfect squares out of the root. That's what we're doing here. We're pulling out perfect squares. So if you got 3 root 6, good job. Now I want you to be aware that there are multiple ways to pull out perfect squares. One of the factorizations that we used for root 54, or for 54, was a 3 times 18. We could have proceeded with that factorization and used it in the root. So this would have worked because we do have a perfect square in 18, but it would have required more steps. So let me show you what I mean. So let's say we have root 54, and then it becomes root 3 times 18. So we have root 3 times root 18. Well, in this case, we can actually pull out the perfect square in 18. So we have root 3, and then root 18 becomes 9 times 2, so the 9 is there. So then, using the green principle, we take root 9 times 2, and we break it up into 2 roots. So we have root 9 times root 2. And then root 9, the middle number, that's a perfect, because 9 is a perfect square, we get 3. And then you just multiply the root 3 and the root 2 to get root 6. And we haven't learned how to do that, but to multiply roots at this point. But that's just another way to do it. But that's not the best way to do it, because look at all the steps. Those are a lot of steps there. So you want to avoid doing it that way. You want one number that's a perfect square and another number that is not a perfect square and does not contain a factor that is a perfect square. So if you don't understand what I mean by that, don't worry, we're going to do some more problems and you'll see what I'm talking about. There's there's little details that students miss when it comes to these problems, and it really causes them a lot of confusion. So, but if you got 3 root 6 for number 29, good job. All right, so let's see if you can do number 30. And when you come back, we'll do it together. All right, we're back. So 4 times 5. 4 is a perfect square, and that's why I factored it to 4 times 5. I could have factored it to 2 times 10, but I chose 4 times 5 because 4 is a perfect square. Use the green principle to break it up. And then root 4 is 2, so we pulled out a perfect square. We cannot pull out anything other than perfect squares, so that's why we need these yellow numbers. We're looking for those yellow numbers. All right, so let's see if you can try number 31. Let's see what's going on with number 31. In fact, you know what? Let's try number 31 together. I want to demonstrate a point here. So we could try 5 times 8. But the problem is it would require 2 steps, like I was demonstrating on problem 29. So we don't want to do that one. We don't want to do 5 times 8 because we have a number that's not a perfect square, and we also have another number that's not a perfect square, but this number contains a perfect square if you factor 8, because 4 is a factor, so it contains 4. But we don't want that. We want a factor so that one number is a perfect square and the other number is not a perfect square, and it doesn't contain a perfect square as a factor. So that's what we have here. So square root 4 times 10 is what we need. So go ahead and continue with that with pulling out the perfect square, and when you come back, we'll do it together. All right, we're back, so use the green principle. When I say the green, I'm talking about this thing over here. That's what we're using to break it up into 2 roots. And then you get 2 root 10. So if you got 2 root 10, good job. All right, try number 32, and when you come back, we'll do it together. All right, we're back. So 9 times 5 is what we're looking for. We could have used 3 times 15, but again, these are not on the yellow list. We're looking for a perfect square. Use the green principle. And we have 3 root 5. So if you got 3 root 5, good job. So again, there are many different ways to factor, but you need to factor in a way that makes it easiest for us to pull out a perfect square. So again, if you try some factorization and it doesn't work, that's okay. Just find a different factorization. All right, so now we could try 3 times 8 for 33, but that's not really, it's not going to work because even though there's a perfect square inside 8, 8 is not itself a perfect square. So what else can we do? Try 33, and when you come back, we'll do it together. All right, we're back. The best factorization, the only factorization that's going to work is 4 times 6. Actually, 3 times 8 would work. It would just be longer. So use the green principle, and we have 2 root 6. So if you got 2 root 6, good job. All right, try number 34. Again, you want a factorization that's going to make it easiest for us to get to the answer. So try number 34. When you come back, we'll do it together. All right, we're back. So it's going to be 9 times 7. We could try 3 times 21, but 9 times 7 is the easiest way to do it. Use the green principle to break it into parts, and 9 is a perfect square, so we end up with 3 square root 7. Again, what number times itself equals 9? 3 times 3 equals 9, so it's root 9. Square root 9 becomes 3. So if you got 3 square root 7, good job. All right, so try 35. And again, you can use your calculator if these numbers are too big. If you want a factor tree, you can use your calculator. Try dividing by 9. Try dividing by 3. Try dividing by 11. And that will help you construct your factor tree. So try 35. And remember, we're looking for these yellow numbers. We want these yellow numbers as factors. And when you come back, we'll do it together. All right, we're back. So I'm going to use 9 times 11. That's the easiest way to do it. Use the green principle. And 9 is a perfect square, so square root of 9 is 3. So if you got 3 square root 11, good job. All right, so for number 50, I think we've got the same situation, but these numbers are starting to get a little bit more difficult to deal with as far as pulling a perfect square factor out. So at this point, we need to start using more complicated factor trees. So we know 50 is 5 times 10, right? But neither of these numbers are perfect squares. We don't see these numbers on our list. Again, we're trying to pull out a perfect square. We have to identify the perfect square factor first. We haven't identified it yet. So now let's keep going. We have 5 times 2. And again, we still have not identified any perfect square. So a lot of students will get down to this point and they'll say, wait a second, I'm confused. I don't see it. It's not there. Well, you need to understand that sometimes you have to recombine. I can recombine these 5s to make 25 times 2. This 2 remains, but I combined the 5s, I multiplied them back. You see, when you factor, you're dividing. That's why I said use your calculator to divide by 5. To get this factorization, you have to divide 50. So we can go backwards and we can take these 5s and multiply them to get back to 25. So it's true that 5 times 10 is 50, but it's also true that 25 times 2 is 50. So again, you're probably thinking, well, I don't get it. Who cares? Well, the reason we care is because, look, we now have our perfect square. So what this problem teaches us is that sometimes if you construct your factor tree and you don't see anything, sometimes you have to recombine the numbers to see the perfect square. So we're going to use that 25. So we're going to make this 25 times 2. And again, you want to write your perfect square far to the far left here. And we're going to use the green principle. Remember, whenever I say green principle, I'm talking about this thing over here. Break it up into 2 square roots, and square root 25. That's a perfect square. That's the whole point of doing this. What number times itself is equal to 25? Obviously, it's 5. And again, remember, when you put a number right next to a root, it's considered to be multiplying. 5 times root 2. So again, I know this is a lot to take in, but we're going to do a lot. We're going to do a lot of problems. All right. So for number 37, again, there's a lot of different ways to factor, but the easiest way to factor is not going to be exactly obvious. So you might have to factor and then recombine. So construct your factor tree, play around with it, recombine, and see what you can do. But I'm going to show you a way not to do it, because this problem is going to get a little bit more complex. So root 4 times 8, that's the wrong way. Well, it's not technically wrong. It's just it's going to be the long way. You always want to do it the shortest way possible, or else you're going to waste a lot of energy. So you might think to yourself, I did it. I succeeded. I found a perfect square. And that is true. 4 is a perfect square. You can see it on the yellow list there. So then we use the green principle, or the green rule, whatever you want to call this. And root 4 becomes 2, and we pulled out a perfect square. And you say, see, I'm done. There we go. The problem is there's a perfect square that's in 8. You see, we did root 8 up here, and it became 2 root 2. So we didn't really pull out all the perfect squares. You have to pull out all the perfect squares. So this is the incorrect way to do it. Now you can keep going and pull out the perfect square in the root, but again, we don't even have enough room to keep going on that. So you want to do it the easiest way possible. So the easiest way possible is to take 32, and we know that's 4 times 8, but then continue to factor. 8 becomes 4 times 2, and now you're going to recombine the 4s. 4 times 4 is 16, and now that's the factorization we're going to use. Because this is a perfect square, it's in our list, our yellow list, and this number does not contain a perfect square. It's neither a perfect square, nor does it contain a perfect square as a factor. So this is the quickest way to do it. So we're going to use 16 times 2. So again, I know this is a lot to take in, but we're going to do a lot of practice problems. You're going to get the hang of it. So now we're going to use the green principle. And square root 16, what number times itself is equal to 16? That's 4. And there you go. So that's the fastest way to get to the answer. So whenever you factor, you're looking for one number that's a perfect square, and the other number has to be neither a perfect square, nor should it contain a perfect square as a factor. So I know that's kind of complicated to take in all that information. But again, we're going to you want to factor and get your answer as quickly as possible. You don't want to have to keep factoring out more and more perfect squares as you go, because that's just going to take a lot of time and energy. All right, so I'm going to put my equations down there, and for number 38, that's going to be pretty easy, because there's really only one factorization that's going to give you a perfect square. So again, don't be afraid to use your calculator. You're going to have to do a factor tree on that and divide 125, but you know it's going to be divisible by 5. So try dividing 125 by 5 so you can figure out what the factor tree is going to be. 5 times what is equal to 125. Try 38. When you come back, we'll do it together. All right, we're back. So it's going to be 5 times 25. So if you divided 125 by 5, you got 25, which means that 125 is the same thing as 5 times 25. But I'm going to put the 25 first, so I don't come into problems with the order when I pull out my perfect square. So then use the green principle down below, break it into two roots, and square root 25 is 5. So you should end up with 5 root 5. So if you got that answer, good job. Now for number 39, again, you could factor it to 4 times 20, but the problem is there's a perfect square in 20, so you'd have to pull out a perfect square again. You'd have to pull out one here, and then you'd have to pull out one here. You don't want to do that. So try to find the fastest way to pull out a perfect square using your calculator. Well, actually, you don't really need your calculator because you can just factor it to 4 times 20 and then factor 20 and then recombine. So try that, and when you come back, we'll do it together. All right, we're back. I'm just going to move this stuff over a little bit. So we could try 4 times 20, but that's not the best way to do it. What we want to do is we want to factor 20 to 4 times 5. Then we're going to recombine the 4's to get 16 times 5. And that is the best way to do it. So we're going to change 80 to 16 times 5. And then we're going to use the green principle. I'm going to keep that in my window. And we get 4 root 5. That's the fastest way to get to the answer. Now, if you used root 4 times 20, you would get to the answer. You would find the correct answer. It would just take a lot longer, because now you have to pull out a perfect square at a 20. So then you factor that to 4 times 5 and use the principle, the green principle. And then root 4 is 2. And then you have to combine the 2 and the 2 to get 4. 2 times 2 is 4, and then you get 4 root 5. You get the same thing. But look, it just takes so much longer. So it's really important for you to use the shortest method possible. And you find the shortest method by using your factor tree, and you can recombine if you need to. So again, I know this is a lot to take in. Students typically do not like square roots. They're afraid of them. They're scared. But there's no need to be scared because you're going to get a lot of practice today. So try 75. You may need to use your calculator for that one, because we don't have a multiplication fact for 75. So try 75, use your calculator if you need to, divide by whatever number, and when you come back, we'll do it together. All right, we're back. So if you divide 75 by 3, you get 25. So we know that 75 is 25. Whoops. We know 75 is 25 times 3. Use the green principle. And the reason we pulled out 25 is that's a perfect square. It's one of the numbers in the yellow list. So I'm sorry if I'm talking too much, but I'm just trying to make sure that you understand what's going on here. If you're tired of me talking and you think you understand this, that's okay. Just fast forward. Don't listen to me talk if you understand this. All right. So for number 41, I just want to give you a hint. If you use 6 times 8, that's going to take a lot longer. So you want to use a different factorization. So start off with 6 times 8, but then you want to recombine to find a perfect square, because neither 8 nor 6 are perfect squares. Or excuse me, you want to keep factoring, but you want to recombine so that you have a perfect square, and a number that's not a perfect square, neither does it contain a factor that's a perfect square. So try 41. And if you're still a little fuzzy about what exactly I'm talking about, again, don't be worried, because this is a lot to take in. So just try your best. Try number 41, and when you come back, we'll do it together. All right, we're back. So if I do 6 times 8, that's 48. But that doesn't help us because there's no numbers in the yellow list. So I'm going to factor, as I showed you, to 2 times 4. Then I'm going to, let's see, what should I do here? Then I'm going to have to keep factoring. So I'm going to factor 6 to 2 times 3. And just bring down the 2 and the 4. And so now I'm going to combine all of the 2's. 2 times 2 is 4, and then times 4 is 16. So I'm combining all those numbers, so I now have 3 times 16. So again, I combined, I took, this can get really confusing for students. I multiplied 2 times 4 to get 16, and the 3 just remains. So we learned how to do factor trees in my arithmetic course, but we didn't necessarily learn how to recombine. A lot of students don't learn how to recombine. So you can recombine, and now we have 3 times 16. Now you're probably thinking, okay, well, why do we know 3 times 16 works? Well, because 16 is a perfect square. That's one reason we know it works. But we also know that this number is not a perfect square, neither does it contain a factor that is a perfect square. If we had root 16 times 8, this would be a perfect square, but we'd have to keep going after pulling out the 16 because 8 contains a perfect square also. So the ideal situation is to have a perfect square and a number that's not a perfect square, nor does it contain a factor that is a perfect square. When you have 16 times 8, you have a perfect square, but you also have a number that contains a factor that's a perfect square. We don't want that because that means we have to do more steps. So now we're going to use the green principle, break it up into 2 parts, and square root 16 is 4, and then we're done. So that's why we use that factorization, is we got to the answer very quickly. It didn't seem like we were going very fast because I was talking so much, but again, it takes longer for me to do this because I'm explaining what I'm doing. When you do the homework, you're going to do it much faster because you don't have to explain it to anybody. All right. Sometimes students get the idea that math takes a long time because their teacher is yapping and he has a mouthful of words trying to explain this stuff, but you don't have to explain it. You just have to do it. All right, so 96. You might need your calculator for that one. Do a factor tree and try to divide by some numbers and figure out what the factorization would be. Pull out your perfect square, and when you come back, we'll do it together. All right, we're back. So if I divide by 3, I get 3 times 32. We don't have a perfect square at this point, so we need to keep going. I'm going to factor 32 to 4 times 8. Now we have a perfect square, but the problem is I know that I have a perfect square in 8 too, so I'm going to have to factor 8. Again, you have to pull out all the perfect squares, so I'm going to factor 8 to 2 times 4. And, whoops, I don't know why I did that. That should be a 4 there. And so now I'm going to recombine. I'm going to combine the 4 and the 4 to get 16. So 4 times 4 is 16, and 2 times 3 is 6. So I'm left with 16 times 6. So now I have a perfect square. And I have the other number is neither a perfect square nor does it contain a factor that's a perfect square. So it's 16 times 6. That's the factorization we're looking for. Again, I'm just showing you the fastest way to do it. All right, so now we use the green principle. And again, you want to write the perfect square on the left. It just makes it easier. And we end up with 4 root 6. So if you got 4 root 6, good job. All right, so why don't you try number 72? Again, you got to try a lot of different factorizations. Try 72, and when you come back, we'll do it together. All right, we're back. So we could try 9 times 8, but the problem is we have a perfect square and a number that contains a perfect square as a factor, so we don't want to do that. We want to keep factoring and then recombine. So I'm going to keep factoring. I'm going to make 8 4 times 2, and then I'm going to combine these numbers to 36. And now we have a perfect square. 36 is in the list of our yellow numbers there, right here. And 2 is neither a perfect square, nor does it contain a perfect square as a factor. So 36 times 2 is the quickest way to get our answer. So we're going to change that to 36 times 2 using the green principle. We're going to change it to root 36 times root 2. And we pulled out the perfect square because what number times itself is equal to 36? 6. 36 is a perfect square. That's why we pulled 36 out, because it's a perfect square. So if you got 6 root 2, you're doing really well. If you didn't get 6 root 2, then that's okay. We're going to do more problems. So 112, I know I got to get my calculator out for that one. I don't know what goes into 112. So this, I know it's even, so I know I can divide it by 2. And I get 2 times 56. Now 56, that's one of our multiplication facts. I know that's 7 times 8. But notice that there are no perfect squares here. So now I have to keep factoring. Whoops. To keep factoring. And now I have a perfect square, but there are other perfect squares. We don't see them, but if you combine these 2's, you get another perfect square. So again, you have to pull out all the perfect squares. So let me show you what I mean by that. If I take the 4 and then I combine all these numbers, if I combine 2, 7, and 2, multiply them all together, then that would be 28. So this is a perfect square. The problem is the other factor contains a perfect square as a factor, so I wouldn't be pulling out all the perfect squares. So I can't do that. So what I'm going to do is I'm going to combine the 2, the 4, and the other 2. 2 times 4 is 8, times 2 is 16. And I'm just going to rewrite the 7. And so now I get the factorization 16 times 7. So the whole reason we did that was to get this factorization. Whoops. To come up with this factorization 16 times 7. Because now we have a perfect square, which is 16, and a number that is neither a perfect square, nor does it contain a perfect square as a factor. So 16 times 7 is the easiest factorization. It's not the only factorization that will work. It's just the best factorization to use, because you can get to the answer much quicker. So if you got 4 root 7, good job. All right, so on to number 45. So hopefully you understand how to recombine, how to factor, how to keep factoring and recombine. You just have to play around with this stuff. You know, you're gonna factor, and you're not gonna come up with the right answer. You're gonna have to use trial and error, and just play around with this stuff until you find the right factorization. Don't be discouraged if you come up with a factorization that doesn't give you the simplified answer. We want to take as many square roots out as we possibly can. Just try your best, and if you make a mistake, you can watch me, and you'll start to get the hang of this. So why don't you try 45? You're going to need your calculator probably to divide that, to use a factor tree, and when you come back, we'll do it together. All right, we're back. So 108, I'm going to divide by 2, and then I get 54. And then 54 is good because that's one of our multiplication facts. Now I have a perfect square, but if I combine, I get 12 times 9. The problem with that is 12 contains a perfect square. So we have to keep going. So, and the reason it contains a perfect square is because I know it factors to 4 times 3. So, let's see here. So I'm going to keep going, and then I'm going to combine the 4 and the 9 to get 36. And I'm going to just rewrite the 3. So that's what we want, 36 times 3. And why do we want that factorization? Because 36 is a perfect square, and 3 is neither a perfect square nor does it contain a perfect square as a factor. So then we use the green principle, break it up, and we have 6 root 3. So if you got 6 root 3, good job. All right, so try number 46, and when you come back, we'll do it together. All right, we're back. 124, I'm going to divide by 2, and that way we get 62, I think. Yep, 62. And I'm going to have to continue, so that would be 2 times 31, and that's not one of our multiplication facts, but you can just use a calculator. Combine the 2's, 2 times 2 is 4, and we have a number that's a perfect square and a number that's neither a perfect square nor does it contain a perfect square as a factor. So 4 times 31 is going to be the correct factorization, or the factorization that gets us to the answer as quickly as possible. Use the green principle, break it into two roots. We have a perfect square, so square root 4 becomes 2. And there we go. So if you got that answer, good job. All right, try number, again, we're factoring out a perfect square here. We're making the expressions simpler. So try number 47, or yes, number 47. When you come back, we'll do it together. All right, we're back. So 150, that would be 3 times 50, I know. And we have no perfect squares so far. Let's try 5 times 10. And at this point, we still don't have any perfect squares. So this is a case where I would have to recombine. So I'm going to keep factoring before I recombine. 10 is 5 times 2. So now I can combine the 5's. Combine these 5's to make 20. So we're going in the opposite direction now. So 5 times 5 is 25, and then 3 times 2 is 6. So the factorization is 25 times 6. And why is that the correct factorization? Well, because 25 is a perfect square, and the other number is neither a perfect square nor contains a factor that's a perfect square. So that's why I know that that's the best way to do it. Use the green principle. And square root 25 is 5, and we end up with 5 square root 6. So if you got 5 square root 6, good job. All right, so try number 48, and when you come back, we'll do it together. All right, we're back. So I'm going to try 2 times 81. Bingo. That was quick. And again, you can just divide 162 by 2 to get 81. This is a perfect square, and this is a number that is neither a perfect square nor does it contain a perfect square as a factor. So I'm going to break that into 81 times 2. And now we can use the green principle. And square root 81 is 9. And there we go. So 9 square root 2. So if you got 9 square root 2, good job. You're getting the hang of it. If you're not getting the hang of it, that's okay. We're going to do more problems. Try 49, and when you come back, we'll do it together. All right, we're back. I know that 16 times 10 is 160. That's one way to do it. And that's actually it. That's correct. Because we have a perfect square and a number that is neither a perfect square nor does it contain a factor that's a perfect square. So we're going to make that 16 times 10. Use the green principle. And we have 4 root 10. And there you go. So if you got that answer, good job. Try number 50. And when you come back, we'll do it together. All right, we're back. So again, there's many different ways to factor these things. So you gotta just try some different factorizations. So I'm gonna get my calculator because I don't know what to deal with when it comes to 176. I'm gonna try dividing by 4. I get 44. So you divide it by 4, you get 44. So 4 is a perfect square, but the problem is this number contains a perfect square as a factor. So we're going to keep going. We're going to factor 44 to 4 times 11. And so you can see we have 2 perfect squares here. So we're going to have to recombine these to make 16. And now we have 16 times 11, so we have exactly what we want. We have a number that's a perfect square and a number that's neither a perfect square, nor does it contain a factor that's a perfect square. Again, that's just the easiest way to do it. Not the only way to do it, but the easiest way to do it. So 16 times 11. All right, so use the green principle, so on and so forth, and we get 4 root 11. So we got 4 root 11. Good job. Try number 51, and when you come back, we'll do it together. All right, we're back. You could do 18 times 10, but 18 is not a perfect square. So we're going to have to keep factoring. And you can see now we have a perfect square, 9. But there's other perfect squares too. If you recombine the 2's, 2 times 2 is 4. That's a perfect square. So then you want to recombine these squares and you get 36. That's another perfect square. So now we have 36 times 5. So why is that the factorization that we're looking for? It's the factorization because we now have a number that's a perfect square and a number that's neither a perfect square nor does it contain a perfect square as a factor. So use the green principle over here, and we have 6 square root 5. So if you got 6 square root 5, good job. All right, so again, we're doing a lot of factoring, a lot of different things here. Just try your best to make a factor tree, and go ahead and attempt 52. When you come back, we'll do it together. All right, we're back. So we're going to break 200 into, let's see, 20 times 10. We can try that. But neither of those numbers are perfect squares. So we're going to have to break 20 into 4 times 5. And now we have a perfect square. But if you recombine 5 and 10, we have a number that contains a perfect square as a factor. And you're probably thinking, well, how do you know that? Well, I know that 25 times 2 is 50. That's why. So a lot of this just depends on your experience with the math. You may get to 4 times 50, and then you'll square root that, and you'll end up with 2 square root 50 and think that that's going to be the answer, but that's not the answer because you have a perfect square inside the 50, and that's what really confuses students. We're going to I got lost there. I erased all my stuff. So we're gonna factor to 2 times 5, and we're gonna combine the 5 and the 5, and we're also gonna combine the 4. So 5 times 5 is 25. 25 times 4 is 100, and so we end up with 100 times 2. So that's actually the best way to do it. And why is that the best way to factor? Because 100 is a perfect square. That's one of the well, actually, it's not on our list, but you can figure it out just by finding all the squares. We got 49. We got 64. And 9 squared is 81. I'm sorry, I forgot to mention that 81 is on that list too. I think we used 81 in a previous problem. I didn't mention that it wasn't on the list, but again, you can come up with that list yourself. There's no end to the number of perfect squares. I just wrote a random, or the first 7 or 8 perfect squares. So then we go to 10 squared, which gives us 100. So 100 is actually a perfect square. So we use the green principle and break it up, and we get 10 root 2. So we got 10 root 2. Good job. So 100 is a perfect square, and 2 is neither a perfect square nor does it contain a perfect square as a factor. All right, so try number 53. Again, it's okay to use your calculator. You're going to have to divide to construct your factor tree. And when you come back, we'll do it together. All right, for this one, I'm going to go right to the answer. It's 25 times 10. Use the green principle there, and we get 5. Whoops, I forgot to write the root on the 10. 5 root 10. So we got 5 root 10. Good job. Try number 54. You may need your calculator for that one. I'm going to use my calculator. And when you come back, we'll do it together. All right, we're back. 275 divided by 5. I know 5 goes in because the 5 is in the ones place. Or if there's a 0 in the ones place, 5 goes in also. You may have tried 250 divided by 5, and then you'd get the factorization 5 times 50 for number 53. But again, 5 times 50 is not the optimal way to do it. It's not wrong, it's just not optimal because you need to do multiple steps. All right, so when I divide by 5, I get 5 times 55. So I'm going to have to keep going because I don't see any perfect squares. So then I'm going to factor 55 to 5 times 11. And I'm going to recombine the 5s to get 25 times 11. And then you can see we have a perfect square and a number that's neither a perfect square nor does it contain a perfect square as a factor. And because it doesn't contain a perfect square as a factor, we don't have to pull out any more perfect squares, which means we can get to the answer as quickly as possible. So that's 25 times 11. And use the green principle. And we have 5 root 11. So we got 5 root 11. Good job. All right, so now we're going to something a little bit different. Because now you can see that we have a number in front of the root. But that's no big deal. All that means is that when we pull out the perfect square, we're just going to multiply it into that number. So we'll just keep the 3 there, and we'll factor 44 to 4 times 11. And we use the green principle, and it becomes root 4 times root 11. And again, you don't really need dots. But I'm going to use dots once I get rid of the root. So now we have 3 times root 4 is 2, right? Isn't root 4 2? We learned that. So root 4 becomes 2. And I'm going to need a little bit more space here. And then we just multiply the 2 and the 3 to get 6 root 11. So the only difference is when we pulled out the perfect square, we just multiplied it into whatever was in front, and we got 6. So no big deal. It's not really anything that different. So try number 56, and when you come back, we'll do it together. All right, we're back. So I'm going to factor 50 to 25 times 2, because we've already done that earlier today. And then use the green principle. And then we have square root of 25 is 5. And the 5 comes out and it multiplies into the negative 8 to get negative 40 square root 2. So if you got negative 40 square root 2, good job. All right, so try number 57. And when you come back, we'll do it together. All right, we're back. So I'm going to factor 12 to 4 times 3. We've done that one quite a bit today. And I'm going to use the green principle to break up the square root into 2 square roots. And then I know 4 is a perfect square, so that becomes 2. And 2 times 2 is 4, and you're left with 4 root 3. So if you got 4 root 3, good job. Try number 58, and when you come back, we'll do it together. All right, we're back. I gotta stop making my 4s look like 9s. So if you got negative 6 root 5, good job. All right. Now number 59 has some big numbers there. So you might need to use your calculator when you factor, when you use your factor tree. So try number 59, and when you come back, we'll do it together. All right, we're back. So I'm going to try dividing 84 by 4 on my calculator, and I get 21. So it looks like that's going to be it, 4 times 21, because 21 is neither a perfect square nor does it contain a factor that's a perfect square. So now we have square root 4 is 2. Whoops, sorry. And I'm going to move this up a little bit. Whoops. We have 6 root 21. So if you got 6 root 21, good job. All right, so try number 60. And when you come back, we'll do it together. All right, we're back. So I'm going to use 9 times 11. That's just the best way to do it. And again, we don't really need dots when you're putting the roots next to each other or the numbers next to the roots. But once we get rid of that root, you got to use dots for multiplication, or you can use parentheses. I'm just putting dots in here, even though I don't need them. I don't want you to get confused. All right, so 4 times 3 is 12, and our final answer is 12 root 11. So if you got 12 root 11, good job. Try number 61, and when you come back, we'll do it together. All right, we're back. So the best way to factor that is 4 times 10. Use the green principle. And negative 5 times 2 times root 10. And negative 5 times 2 is negative 10. So we end up with negative 10 root 10. So if you got that answer, good job. All right, try number 62, and when you come back, we'll do it together. All right, we're back. Let's see here. 4 times 22, I think, is the only way to do it. Because 22, if you factor it, it's 2 times 11. There's no perfect square. And, of course, 22 is not a perfect square. So use the green principle. So if you got 8 root 22, that's very good. All right. So let's bring this up here. So that was pulling out a perfect square from a square root. So now we're going on to the last thing that we're going to do today, which is adding and subtracting square roots. I'm going to put this down here for now. All right, so now we're going to do something that's pretty easy. You're probably hoping that there's going to be something easy after all that stuff. So we have 5 root 3 plus 7 root 3. That's like saying 5 apples plus 7 apples. 5 apples plus 7 apples is how many apples? In other words, it's like saying 5x plus 7x. It's the same type of thing. That would be 12x. But instead of x, it's root 3. So 5 root 3 plus 7 root 3 is 12 root 3. So that's how you add roots. But just be aware that the only reason that we could add these roots is because they're both the same. You see? If you had different roots, you could not add them. In the same way that you cannot add 5x plus 7y. These are different, so you can't add them together. You can add them, but you can't combine them into one expression. That's what I really mean. So why don't you try number 64? What is 8 apples minus 2 apples? But instead of apples, it's root 10s. We have the same root, so we know that we can combine. So try number 64, and when you come back, we'll do it together. All right, we're back. 8 root 10 minus 2 root 10 is 6 root 10. So if you got 6 root 10, good job. Try number 65, and when you come back, we'll do it together. All right, we're back. 7 root 2 plus 3 root 2 is 10 root 2. And rectangle. And there we go. Just waiting for my computer to catch up there. All right, so try to 66, and when you come back, we'll do it together. All right, we're back. 8 root 5 minus 3, that's going to be 5 root 5. So we got 5 root 5, good job. Now we have 3 numbers, but it's the same thing because they're all root 7. So to go ahead and combine those, try 67, and when you come back, we'll do it together. So 8 plus 2 is 10, and 10, and by the way, there is no number here. There's no coefficient. But in the same way that there's no coefficient for x, it's just assumed to be 1x. So this is minus 1 root 7. So we have 8 root 7 plus 2 root 7 is 10 root 7. And then 10 root 7 minus 1 root 7 is 9 root 7. So hopefully you didn't get tripped up by that. If you did, that's okay. Now you know what the answer is. Try 68. When you come back, we'll do it together. All right, we're back. Negative 54 plus 9 is negative 45. Negative 45 minus 2 is negative 47. So that would be negative 47. And again, I got to prevent my 4s from looking like 9s. Negative 47 root 2. So as you can see, when the roots are all the same, adding and subtracting roots is really easy. Try number 69, and when you come back, we'll do it together. All right, we're back. 8 minus 5 is 3. 3 plus 9 is 12. So that would be 12 root 6. Try number 70, and when you come back, we'll do it together. All right, we're back. So negative 3 minus 9 is negative 12. And negative 12 plus 5 is negative 7. Let me rewrite that box. And it looks like that's correct. So for number 71, something different is going to happen. Because for number 71, we have root 17s, but we also have root 14s. So just be aware, you can add the root 17s together, the blue ones, you can add those together. And you can add the green ones together, but you cannot add the blues and the greens together because they're unlike terms. So just be aware of that. So try number 71, and when you come back, we'll do it together. All right, we're back. So negative 5 root 17 plus negative 3 root 17 is negative 8 root 17. So I combined the root 17s. And 4 root 14, and this is a double negative, by the way, so don't be confused by that. We learned how to do double negatives in the previous course, my pre-algebra course. Double negatives just become positive, so that's not going to be 4 root 14, excuse me, that's not going to be 4 root 14 minus 6 root 14. It's going to be 4 root 14 plus 6 root 14. So you're going to add this. So 4 plus 6 is 10. 10 root 14. So if you got that answer, good job. Again, you cannot combine these any further because they're unlike terms. One's root 17 and one's root 14. All right, so try number 72, and when you come back, we'll do it together. All right, we're back. Negative 5 plus negative 4 is negative 9 root 11. So we combine the root 11s, and this is going to be positive 6 root 6 because it's a double negative. 6 root 6 minus 5 root 6 is just 1 root 6, but instead of writing the 1, we just write root 6. So if you got that answer, good job. All right, so on to 73. So these are the last types of problems that we're going to do. We're going to add 5 root 3 and root 12. The problem is these roots are different. One is root 3 and the other is root 12. So we cannot add those terms. But if we pull out a perfect square out of the root 12, then this term will become a root 3 term. And we know how to do that because we pulled out perfect squares in the previous problems. So if we factor 12, it becomes 4 times 3. And again, we don't want 2 times 6, we just want 4 times 3 because we have a perfect square. And a number that's neither a perfect square nor contains a perfect square is a factor, because that's going to get us to the answer quickest. So then we use the green principle, so I should bring down my principles here, or my rules, my equations. We use the green principle, whoops, sorry about that. The green principle tells us that we can separate it into root 4 times root 3. And then we have 5 root 3. And root 4 is a perfect square, so that becomes 2. So we pulled out the perfect square. So now you can see we can combine these roots because they're both root 3s. They're like terms. So 5 plus 7 is, or excuse me, 5 plus 2 is 7. So the answer is 7 root 3. So let's try a couple more of these before you try one on your own. Just want to make sure that you got these. I'll put this up here. So I'm going to factor to 9 times 6, and here I'm going to factor to 4 times 6. Again, you want to be aware of the correct factorizations, the ones that get you to the answer as quickly as possible. Then I'm going to use the green principle. I got to write more legibly here, sorry about that. Again, you don't really need dots in between the, whoops, put a dot there instead of a plus sign. You don't really need dots between the roots. All right. So I think that looks correct. So now root 9 is 3. And root 4 is 2. And 3 times 2 is 6. And now you can see that we have all the terms are root 6's. So 3 root 6 minus 6 root 6 is negative 3, and negative 3 plus 2 is negative 1. So we have negative 1 root 6. So let me just double check that. Negative 6, negative 3, that looks correct. All right, so again, we're just doing the same thing we were doing before, except we're using the principle of pulling out a perfect square to combine terms. So we cannot combine these terms because we have a root 2 and a root 18. We can't add those. They're unlike terms. So pull out a perfect square here so that we can combine those terms. So try number 75. If you get stuck, we'll do it together. All right, we're back. Again, you can factor 18 to 6 times 2, but that's not, there's no perfect squares. 6 and 3 are not perfect squares. All right, then we end up with 5 root 2 and 2 times 3 times root 2. And 2 times 3 is 6. And so now we have root 2 terms. So 5 plus 6 is 11. We get 11 root 2. So if you got 11 root 2, good job. So now why don't you try number 76, and when you come back, we'll do it together. All right, we're back. So we're going to pull out a perfect square in 8, root 8, and a perfect square in 32. Now, you could write 32 as 4 times 8, but that's not the quickest way to do it. The quickest way to do it is to factor so that you have a perfect square, 16, and a number that's neither a perfect square nor contains a perfect square as a factor. All right, so then we use the green principle, which you should know by heart probably by now. We're just going to break those, or that square root into 2 parts. And square root 4 is 2. Square root 16 is 4. And then we're just going to combine the factors. 2 times 2 is 4. 3 times 4 is 12. And now you can see that we have root 2's. So 4 root 2 minus 12 root 2 is negative 8 root 2. Negative 8 root 2 plus 1 root 2 is negative 7 root 2. Again, it's extremely important for you to understand that this is 1 root 2, even though there's no 1 coefficient. So if you got that answer, good job. On to number 77. Try 77, and when you come back, we'll do it together. All right, we're back. And I'm going to bring my green principle over here. Where is that stuff? I know you probably know this stuff by heart by now, but I'm just going to bring it. So now we have root 2 terms. And we're ready to go ahead and combine. 9 minus 7 is 2. 2 plus 30 is 32. So we have 32 root 2. So if you got 32 root 2, good job. All right, try number 78. And when you come back, we'll do it together. All right, we're back. And 75 is going to be 25 times 3. That's the best way to do it, not the only way to do it. Actually, that is the only way to do it. Sometimes you have multiple ways to do it. Sometimes there's only one way. And we're going to use the green principle. Break it up into 2 roots. And let's see here. 2 minus 35 is negative 33. Negative 33 plus 8 is negative 25. And keep your root 3 there, because we're combining root 3's. So if you got negative 25 root 3, good job. That means you're getting the hang of this. So it looks like we have 8 more problems. I'm not sure if we're going to get through all these, but we'll come close. So try 79, and when you come back, we'll do it together. All right, we're back. Again, I know the best factorizations to use, so I'm just using the best factorizations possible. You might use different factorizations, but it's just going to take longer to solve the problem. Or to simplify. Let me just double check that everything looks right. So now we have all root 11, so we can combine. Negative 8 minus 14 is negative 22. Negative 22 plus 18 is negative 4 root 11. So if you got negative 4 root 11, you're way ahead of the game. Good job. All right, so go ahead and try number 80, and when you come back, we'll do it together. All right, we're back. And I think we're going to use 16 times 5. That's the best way to do it, not the only way to do it, but the best way to do it. Now we have root 5s, and we get negative 16 it looks like. Negative 16 root 5. So we got negative 16 root 5. Good job. All right, on to number 81. Go ahead and try number 81, and when you come back, we'll do it together. All right, we're back. And we can just get rid of that plus negative. It's not really necessary. All right, so we got negative 26 root 5. Good job. Try 82. When you come back, we'll do it together. All right, we're back. Just double checking that. Everything looks right. You can choose to keep the parentheses in the negative, or I mean the parentheses in the positive if you want, or you can just get rid of them. Doesn't matter. All right, so now we have root 10s. 3 plus negative 30 is negative 20. Negative 27. Negative 27 plus negative 12 is negative 39, I believe. Yep, I think that's correct. Negative 39 root 10. And on to number 83. Go ahead and try number 83. And when you come back, we'll do it together. All right, we're back. And if I remember correctly, I think this is going to be, Actually, I don't remember what that's going to be. So let's get out the calculator. 112 divided by, let's try 4. So it's going to be 16 times 7, I believe. 16 times 7, that's going to be, yes, 16 times 7. All right, let's just double check. Everything looks right. Combine. Negative 51 root 7 is what I got. So if you got that answer, good job. Make sure your negative is nice and dark there. There we go. All right, try 84, and when you come back, we'll do it together. All right, we're back. And I get negative 19 root 7. So if you got negative 19 root 7, good job. Yep, that looks correct. So for number 85 and 86, the last problem's here. There's something different going to happen. So let's do 85 together, and you can do 86. So same situation. We're just pulling out perfect squares. And we have 27 root 5 plus root 7 minus 2 root 5 plus 4 root 7. So what is the big difference here? Nothing seems different at this point. We've just done the same thing we've done for all these problems. Well, the difference is that now you have root 5s and you have root 7s. So be aware that you can only add the blue numbers and together and yellow numbers together, but you cannot add blues with yellows. So 27 minus 2 is 25 root 5, and 1 root 7 plus 4 root 7 is 5 root 7. And you just have to leave it like that. There's nothing you can do with it beyond that point. So again, the principle there is that if you end up with different roots, you cannot add them together. That's very important. So try the last problem, number 86, and when you're done, we'll do it together. All right, we're back. me just write that a little better there. All right. And we're almost done here. And as you can see, we have root 3's and we have root 2's. So you can only combine the blue numbers and with other blue numbers and yellow numbers with other yellow numbers. So -5 plus 3 is -2. And -24 plus 1 is -21. And that's all we can do. So let me just double check. Whoops, that shouldn't be 21. I'm sorry. That should be 23. So if you want to take screenshots of all the work that we did today, go ahead and do that now. Here's the first 2 pages. And the second 2 pages. And the last 2 pages. Also, if you want to take screenshots of the equations, or the 2 important equations and the perfect squares, go ahead and do that. But before you go, be sure to get screenshots of the homework. Here's the first 2 pages. And the last page. And remember, your homework has to be complete, correct, neat, and in order in your binder. If any one of those characteristics doesn't fit your homework, then it's pretty much a waste of time. And if you don't do the homework at all, it's a guarantee you're going to learn absolutely nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.